Hi guys, so this video we are going to go over energy diagrams as well as thermochemical stoich. So we're going to start with going over energy diagrams. So basically what an energy diagram is, it's sometimes also called a potential energy diagram, is it's basically a visual representation of the energy change that occurs during a chemical reaction. So an energy diagram plots the energy change that occurs during a chemical reaction. And it looks like this. This one is actually an exothermic potential energy diagram, and we'll kind of talk through how we know that as we go. So we're going to start right here with A. So right here, A on our graph represents our energy or heat of our reactants. Remember, those words are kind of used interchangeably in this unit. So you may see energy, you may see heat. They're just kind of used interchangeably there. Next, we have right here, B. It's this hump up to our top spot. That is our activation energy. That is the energy required to get our reaction to start. So whether it's an endothermic or exothermic, all reactions have an activation energy, just the amount of energy you have to put in order to get your reaction to go. So that's our activation energy. I'm going to skip a little bit and I'll come back to them. And then I'm going to come over here to E. Oops, I meant to make that highlighter. To E over here. And E is the energy or heat of our products. So energy or heat of our products. All right, now that we know that, we'll look at D right here. D goes between our products and our reactants, and D is our delta H, or our change in enthalpy, and our change in enthalpy is equal to, if you remember from yesterday, the energy of your products minus the energy of your reactants. So delta H is equal to P minus R. So that's our delta H. It's also called the enthalpy of our reaction. It's how much energy is gained or released during a chemical reaction. And then finally, last but certainly not least, right here, we have C. And C is kind of the, C is right there. And C is our activation energy of our reverse reaction. It's called EA, and then it has like a little prime on it. So activation energy of our reverse reaction. I do want us to label one more point on our graph, and that's going to be up here at the very top. So I'm just going to put a little X on it, and X is known as our activated complex. It's just the very topmost point on our energy diagram up there of our activation energy, the very topmost point. It's called the activated complex. Okay, so let's kind of talk through how these graphs can look different and all of that fun stuff. So first off, what is the activation energy? I kind of talked about it a little bit, but it is the amount of energy required to start a reaction. So just how much energy do we have to put in? Like I said, whether it's endo or exo, releases or requires energy, all chemical reactions do have an activation energy. It's just in an exothermic reaction, typically you can get the energy you need from the surroundings for that reaction to take place. Okay, so now we're going to look at how endothermic and exothermic reactions are different and look different in their graphs. All right, so we're going to start with our endothermic here. So endothermic, we have to put energy into it. And so basically that kind of tells us then, since we have to put energy in, that the energy of our products is going to be greater than the energy of our reactants. So energy of our products, we can see on our graph here, the products are higher than the reactants. So our products have more energy. So in order to get there, we have to put energy in. So energy is absorbed. Again, we're putting energy in. So it goes from our surroundings into our system, and delta H is positive. Now, I always think of and remember graphs based on roller coasters. So endothermic reaction is going to be a really boring roller coaster. All right, so let's say you're on a roller coaster. We're going up this giant hill. Like, this looks like it's going to be so much fun, right? So good. And then we get to the top and whomp, there's almost nothing. That's like a really lame roller coaster. So since you put a lot in, didn't get a lot out, that would be an endothermic reaction. So endothermic is a lame roller coaster. Now, let's look at exothermic. So in an exothermic reaction, our reactants are going to have more energy than our products. So reactants will be greater than products. So that means energy is released. We release energy to our system because our reactants have greater energy than our products. So our energy goes from our system into our surroundings, and delta H is negative. Now, I identify this as an exothermic because it's exciting. Exo, exciting. I just think it works for me. But here we go. So for exothermic, we're just barely climbing up anything. And then, woo, we get to go on a nice, fun, long roller coaster ride. So exothermic is an exciting roller coaster. All right. Now then, this is just kind of talking through a little bit of stuff we need to know to understand our kind of reverse activation energy, but also just define a reverse reaction. So basically in a reverse reaction, our products, we start with our products and they turn back into our reactants. So it's just flipping your reaction there. I always think of like photosynthesis versus cellular respiration. Those are reverse reactions of each other. But start with your products and they turn into their reactants. And they're going to be opposite. So if your forward reaction is exothermic, your reverse will be endothermic. The forward is endothermic. The reverse is going to be exothermic. And kind of the last thing we're going to talk about with these energy diagrams before we move on to some practice is the activation energy. So remember, activation energy is the energy required for a reaction to start. We can lower that by adding a catalyst. So a catalyst, what it does is it's going to lower the activation energy, and then that will in turn increase the speed of the reaction. Now, it doesn't actually change the difference in energy between our reactants and our products. It just lowers the amount of energy we have to put in to make it start. So you can see right here, our uncatalyzed pathway goes up there, and it's nice and tall. Our catalyzed pathway just lowers that activation energy and makes our reaction happen more quickly. All right, let's do some practice over this. So we're going to start by answering these first ones. So the first one says, what is the activation energy of this reaction? All right, so our activation energy is basically from our energy of our reactants to that topmost point up there. So from our energy of our reactants, that's at 60. Our topmost point is at 120. So the difference between those 60 and 120 would say that our activation energy is 60 kilojoules, because I had to go up 60 kilojoules to get to that top point. Next question says, what is the delta H of this reaction? Well, remember that delta H is equal to the energy of our products minus the energy of our reactants. So in this case, the energy of our products is 40 from our graph, minus the energy of our reactants, which is 60. So that gives us that our delta H is negative 20 kilojoules. So since it's negative, our delta H is negative. I'm going to skip to question 4, and we're going to say that this reaction is exothermic. So exothermic. And then it says, is the system gaining or losing energy? So in our exothermic reaction, we flow from the system to the surroundings. So our system would be losing energy. Okay, so it's just kind of reading the graph on this one. Now, on the next example, I'm going to have you guys try to do it on your own. I know it might be a little hard, but you guys are going to try to draw a diagram that actually represents the reaction below. I'm going to have you guys try to do it, and then I'll go through and go over it with you guys. Now, I want to give you guys some help and some reminders. So when we're missing things, sometimes what can be helpful is to remember these equations. So remember that delta H is equal to our products minus our reactants. And then this one's also just helpful in general. So our activated complex is going to be equal to our activation energy plus the energy of our reactants. And our activated complex can also be equal to our reverse activation energy plus our products. So those may help you. Those equations may help you in figuring this one out. I will go over it with you guys after you've done it. So go ahead and pause the video, try to work through this one, and then I'll go over it. Okay, so my scale on my graph is terrible, but that's okay. So first thing I did is I noticed that it said our reactants begin with 120 kilojoules of energy. So that's easy. I just know that my graph needs to start at 120. Then it tells me that our activation energy is 180 kilojoules. Now, that tells me how far I'm going up from my reactants. So to get to my topmost point, I added my energy of my reactants plus my activation energy, and it told me that my topmost peak would be at 300 kilojoules. So then I went ahead and went all the way up to 300 kilojoules. And then it told me my delta H. So I don't know what my products are, but I do know the difference in energy between my products and my reactants. So delta H is equal to P minus R. So 30 equals P minus 120. So then the energy of my products was 150 kilojoules. So then I just went back down to 150. So make sure that you are using the values that they give you. It's going to be it's going to make it a lot easier for you. All right. Okay, so now we're going to shift and we are going to talk a little bit about thermochemical stoich now. All right, and what we're going to learn is we're going to learn kind of a new mole to mole ratio. And instead of using moles of one substance to moles of another, we can actually use our energy as what we're converting to in these kind of problems. So we are going to use this equation and talk through these next few questions. So first off, I want to notice that I do have energy in my equation. It is a reactant, so that is an endothermic reaction because energy is a reactant. Okay, so our first question says, using the following thermochemical equation, how much heat is needed to make each mole of O2? Okay, so I can actually solve this just like using my kind of mole to mole ratio. So if I want to know how much heat is used to make each mole of O2, well, I can look at my equation. So I'm starting with 1 mole of oxygen. And according to my chemical equation, I'm going to do my molar heat ratio. It's not a real word, guys, just so y'all know, but it does help you kind of define it. I can see that for every 5 moles of O2, it requires 1,170 kilojoules. So instead of doing moles of one substance to moles of another, we can do moles of a substance to energy and use that in place of a mole to mole ratio, in place of the moles on the other side. So for every 5 moles of O2, it requires 1,170 kilojoules. Then I can just solve that by plugging it into my calculator. So 1 times 1,170 divided by 5, and I got 234 kilojoules. Okay, so then my next question says, well, what about 8 moles of NH3? Kind of can do the same thing here. So for every 8 moles of NH3, I can see from my balanced chemical equation that for every 4 moles of NH3, it requires 1,170 kilojoules of energy to make it. And then I can solve it once again. And I got, when I solved that one, 2,340 kilojoules. So really not doing anything terribly different than our normal stoichiometry, other than instead of going from moles of one substance, we go from moles to heat, and we're able to solve it that way. Okay, so now let's jump into doing this with stoichiometry. So what we're going to do is we're going to use previous stoichiometry conversions, so molar mass, mole to mole ratios if we need to, as well as our enthalpy to convert between two substances in the problem. So we're going to start by looking at this reaction. So we have CH4 plus 2O2 yields CO2 plus 2H2O plus 890 kilojoules. So it asks, is this reaction endo or exothermic? So first thing I need to do is I need to find heat. So heat is over here, and it is written in my reaction. It is a product, so that tells me it is an exothermic reaction. And I know it's exothermic because heat is a product. So would this reaction feel hot or cold if you were nearby? It's exothermic, so it is releasing energy, which means that our surroundings feel hot. So this reaction would feel hot to us because it's releasing that energy. And then the last, it asks what type of reaction is this, which takes us back a couple units. But we have carbon, hydrogen, and oxygen. So we see CHO. So we know that this is a combustion reaction. So that takes you back a few units, guys, but it is combustion. Okay. Now let's look at this. So we're going to kind of follow the same steps we would use before. Get to moles, mole to mole ratio. In this case, it'll be our mole to heat ratio, and then get to what the problem is asking for. All right, so this first one says, if you were to react 5 grams of CH4 with excess oxygen, how many kilojoules of energy could you produce? All right, so we're going to go ahead and start by taking what's given here. So I am given 5 grams of CH4. All right, step 1, get to moles. So grams of CH4 is not what I want, so I'm going to drop it low, and I'm going to use my molar mass here. So carbon is 12.01 plus 4 hydrogens, each with 1.01. So that gives me that my molar mass is 16.05 grams of CH4. And my molar mass is always equal to 1 mole. So for every 16.05 grams is 1 mole. Now, moles is not what I want. I want kilojoules of energy, so I'm going to drop it low again, and I'm going to do my mole to heat ratio here. So from my balanced chemical equation, for every 1 mole of CH4, it makes 890 kilojoules of energy. So for every 1 mole of CH4, 890 kilojoules. And then we would solve it. So because that is what we wanted on our problem, we can go ahead and solve, multiply across the top, and divide by the bottom. So I'll give you guys a minute to go ahead and plug it into your calculators. And when I plugged it in, I got 277 kilojoules. Now, because these are endothermic and exothermic, we do need to be careful with our signs. So because this one is exothermic, that energy is being released. So we need to either say 277 kilojoules of energy released, produced, whatever you want to say, or we can also designate that it is being released by saying that it is negative 277 kilojoules. Since we have an exothermic reaction, it would be released energy, so it's negative, since our delta H will be negative. So you can say released, or you can have that negative sign, whichever one is easier for you. Okay, so let's try the next one. So it says, calculate the amount of energy involved when 3.75 moles of aluminum oxide are decomposed. All right, so we're going to take what's given. So we're taking 3.75 moles of aluminum oxide, which is Al2O3. Moles of aluminum oxide is not what we want, so we're going to drop it low. And then since we're looking for energy, we'll do our mole to heat ratio. So for every 2 moles of Al2O3, it's going to require 3,352 kilojoules of energy. All right, so kilojoules is what we wanted. So we can go ahead and multiply across the top, divide by the bottom. So I'll give you guys a minute to plug it into your calculators. And when I do, I got 6,290 kilojoules because of our sig figs. And that would, again, be 6,922. This one is an endothermic reaction since energy is a reactant. So 6,290 kilojoules required. Or the other way we can look at that is positive 6,290 kilojoules. Since it's an endothermic reaction, we have to put that in, so that would be a positive energy value. All right. I want you guys to try this last one. It is a little trickier, but I think you've got it. All right, so I want you guys to try it, see if you can do it, pause the video, and then come back when you're ready to go over it. All right, so this problem says calculate the mass of ethane which must be burned to produce 100 kilojoules of heat. Okay, so this is an exothermic reaction. We have a negative delta H. It's written off to the side. So we do have an exothermic because it's negative. So we are producing 100 kilojoules of heat. So it's actually you can start with negative 100 because we are producing that. So for every negative 100 kilojoules, I then used my mole to heat ratio. So according to our reaction, for every negative 3,120 kilojoules, again, just from our delta H, we need 2 moles of C2H6. Now it asks for mass, so we don't want moles of C2H6, so drop it low, and then used our molar mass to convert to mass of C2H6, multiplied across the top, divided by the bottom, and got 1.93 grams of C2H6 as our answer. All right, guys, that is energy diagrams and thermochemical stoichiometry. Hope this video was helpful. Feel free to email or reach out if you have any questions or concerns, or just stay after next class to talk about it with us. All right, have a great day. Bye, guys.